All right. What can you tell me about arsenic here? It's 33 protons, and if it is neutral, which we're gonna, which it is, how many electrons is that? Okay, and finally, I'm not sure what the atomic mass for arsenic is. We'll say 75. So how would you find the number of neutrons then? 33 from 75. I thought I heard 35. Okay. So, what have we worked with electrons? And the narrator in the video, David Pope, I believe, he said as far as reactivity with any element is determined by which subatomic particle. I think he only said it once, so if you missed it, I get that. What have we been spending the most time on the last couple days? Which deals with which particle? The electrons. And it is the electron that determines an element's reactivity. And that is true. Why would that be, do you think? Why not the protons? Why not the neutrons? Where are they found? Inside the nucleus. So further out from the nucleus, inside the electron cloud, in various specific what levels? Energy levels, these electrons are found. Okay, so when it comes to arsenic, okay, notice we erase the slide rule because you should have that wrote down, correct? Okay, so if we are doing the Bohr model for arsenic, inside the nucleus, we know we've got 33 protons, okay? So, you tell me, how do we start placing these electrons in their various energy levels? You tell me what to do. First energy level, okay? And one thing I want to ask, what predictions can we make with knowing where arsenic is, or any element on that periodic, excuse me, on that periodic table? Why would there be a 4? Okay. What else, what other prediction can you make? Why would we be doing or be concerned about the number 3? Or excuse me, not 3, 5. It's in the 5th column. Okay, it's in the 5th column of the 4th energy level. But what column is it in? Just the P block only. It's in the 3rd, okay, column. So there's a couple predictions that we can make. We're going to see a 2. We're also going to see a 3. Okay, because when you add 2 and 3, surprise, you get 5. That 5, what column is arsenic in? The 5th. Okay, so as we continue on, we've got 1s2, 2s2, 2p6, then what? Okay, now's the tricky part, but the slide rule tells you what to do correctly. And that is what? You're correct. You're right. Why are you right? Correct. Okay? What that means is this energy level actually fill up first. And remember, this is the 1st, 2nd, 3rd, 4th. Okay? And way down here you had that 4s, and 3d is way up here though. But what happens is, remember, this is at the very end, and that's on a different slide. So what that slide rule is telling you, which one of these fills up first? This one does. So it's 4s what? Okay? Now, add all them numbers together. What do we have so far? Okay? How many more do we have to go? 13. Okay? So we're at the bottom of this slide. We go to the top of the next one. Okay? What is that telling you? Which energy level will we be entering now? We did this one already. Now we go up, or excuse me, back down to, and how many columns are in the D block? Okay? Are we going to put all 10 of them in there? So back down to the third. Okay? So now we went from 20, now we're up to 30. Okay? So what comes after 3D10? Okay, 4P6 comes next, but what column in the P block is arsenic in? 3. So 4P. Remember, we said what column in the fourth energy level was arsenic in? 5, right? Well, what happens when you add these two together? That's where our 5 comes from. Okay? Is anyone not making this correlation? Left outside, left middle, left middle, okay, middle, right outside. All right, so what is, we've only said it and done it a 3 times, an electron configuration. This is a Bohr model. An electron configuration is just a linear depiction of the electrons in that element. Okay? So what that means is we would go on with saying, okay, for the element arsenic, okay, we need 33. Okay? We go 1s2, comma, here they are, 2s2, oops, didn't mean to do that. Oh yeah, I'm just running out of room, that's the problem. Okay, so 4s2, comma, 3d what? 10, and then 4p what? Kind of ran out of space here. But when we add all these exponents up, okay, 13, 15, 21, 23, 29, 31, 33. That's what we're looking for, 33. Okay. Now, as you can imagine, the larger these elements are getting, it would take a long time to write all of this out. Well, it does with the Bohr model too, but you can take a factor out of that, and that's what we call a noble gas configuration. Now, we haven't learned what the noble gases are, but it's column 8 on your table or the west wall table. We've already said that arsenic is in column 5, so if we add 3 more columns to that, we're into column 8. So if that's the case, give me an example of any noble gas. Neon's 1. Argon, krypton, xenon, radon, and the lightest of them all, helium. Okay? So what we mean by this, okay, when we factor something out, let's say, I'm just going to put argon right beneath this, okay? Element number 18, okay? One of the things that we can predict with this, okay, what's going to be true about the outer energy level? It's going to be full because argon is in which column? Column 8, okay? And the reason for that is, okay, so if we were to do the Bohr model very quickly, okay, we know 1s2, 2s2, 2p6, 3s2, 3p6. Are we going to go any further? No, because we're already up to 18. 12, 16, 18, and that's all the further we can go. Notice when we say it's in column 8, it comes from adding these two together. Just like we said arsenic was in column 5 from adding those two together. Okay? When we see this, we can correlate this to a filled outer energy level. And the video that we're going to continue is going to state that. We call this a noble gas configuration. And what we do with that is if we were to write this out, okay, 1s2, 2s2, 2p6, okay, 3s2, 3p6. What do we notice about this information? It's all the what? Exact what? It's the exact same. Okay? So when we factor something out of an equation, okay, which you said you had just learned last week, correct, algebra students? Yes? Okay, so when you factor, it's something that they have in common with one another. So these two elements do have something in common, okay, all the way up to here. So rather than writing these elements all the way out like this every time, we can factor the noble gas configuration out of that, which means this. All you would have to write is argon. If we want to do arsenic, element 33, I did that backwards. If we want to do element 33, we would use an argon core, which means we're all the way up to this already, and we have some electrons that are left over, okay, which on the very outside of this box, what do we have left over? What does it tell you on the outside of this box? 4s2, 3d, 10, and 4p what? I don't know how that's showing. I guess it's okay. So now we're already up to 18 because we've proved that with this noble gas configuration. 18 plus 2 gives you what? 20. 10 more gives you 30, and then 3 more gives you. So that must mean this is the same way of writing what arsenic is, but a much shorter way of doing that. Okay? For how many did this sink in and say, this makes sense? Left outside. Because the first time we've seen that. Left middle. Okay? Middle. Right middle. Right outside. Okay? So, let's go ahead and take time to do another example. Okay? What I want you to think about is go ahead and pick any D block element. You can even keep it small. So 21 to 30. Nickel. Element 28, right? See, eventually, like we said, you'll probably get this periodic table memorized because you use it so often. So, you had picked element number 28, which is nickel. Okay? 28. So if we do the electron configuration, we know we start with 1s2. Then what comes next? 2s2. 2p6, okay? Then what? Okay? Okay? what column is nickel in the D block only? Not 10. 8. Okay? So now, we're supposed to get 28. Well, let's see if we can. We've got 4, 10, 12, 18, 20, 28. So that's got to be right. So rather, like I said, rather than doing this every time, what we can do is take this noble gas configuration, which is argon. Okay, so we're already up to 18. So we can make some predictions with that. What period is argon in? Remember, these are your periods all the way over here. And it labels them for you on this table. Argon is in which period? 3. And what block is this over here? It's the P block. So we're already up to this right here because you correctly told me argon is in this period and this block. And we know that noble gas configurations are full. It means this is all the way up to 6. So how much do we have left over past that? So if we were going to take a shortcut, which what this is, what do we have left over past that green vertical line? 10 total, but we want to say it correctly. 4s2, 3d8. These mean the exact same thing. You can always double check. Okay? 18 plus 2 plus 8 more, so this is 20, and 8 more gives you 28. And remember, nickel had an atomic number of 28, so that means this has to be correct. So again, rather than writing these out every time like this, we can take a shortcut with a noble gas. Because you have to pick the next lowest argon. It has to be an element that has a filled outer energy level, and that's what noble gases have. So regardless, let's say we could go even a lot bigger, and let's say we're going to do strontium. We'll keep it really simple. Strontium has an atomic mass of what? 38. Okay? So, what is the next lowest noble gas that has a number lower than 38? Krypton. If you go xenon, you're going up to 54. We want to go down to krypton, and that has an atomic number of what? Remember, we're doing this one 38. Krypton is already up to 36. It looks like it says 35, but it's actually 36. So how many more do we have left to go here? Just 2. So what comes after the period that Krypton is in which period? 4. So what comes after the 4D on your slide rule? Did I look at the wrong? What comes after 4P6? 5s2. Okay? That's all you'd have left to write for that. Rather than writing out 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, then 5s2, all the way out to here, you can say, well, I'm going to factor out a noble gas because I know those outer energy levels are full, which this is. That's all that's remaining. This is something new, and it's probably like, oh my gosh, this is difficult. If you are struggling with this, please get in and talk to me. We're going to continue with this again tomorrow. If you are struggling with this and you're not writing this down, what favors are you doing yourself? None. So I'm just going to walk. I'm just curious to see who's writing this down and isn't. And so we understand this then? No? Okay. We got all this? Are we understanding this? Are we writing it down? Can I see it, please? Okay, where's the examples we just did? Well, where's these new ones? Well, I'm just going by, you told me you're writing all this information down. And you got 2. Okay? You're understanding this? Yeah. All right. Because what would happen if we just said, well, we're going to have a 10.1 problem quiz? How many of you would say, all right, I didn't mean to skip this row. Huh? What's 10.1? Would that be horrible? No? Yes? I'm just asking for input, that's all. Okay. Quick, I'm going to write this down. He's walking around. All right. Okay, so what do you think? What's an example? What do we see as an example of an alloy from yesterday? What does it mean to have an alloy? Metal. A little more specific. You're right. It has something to do with the metal. Brass is a alloy. It's a mixture of copper and what? Okay. So what about steel? Is that an alloy? Well, yes and no, because you're taking iron and you're actually adding copper to it. Okay. So why did the narrator go on to say, well, you can't just use copper and you just can't use tin. If you used too much copper and not enough tin, that bell is probably going to do what? It's going to break. Probably just like what the Liberty Bell did, and that's what they're trying to speculate. Too much tin and not enough copper? It could be. I just remember that it's too much of one and not enough of the other. Okay, so we'll continue with this tomorrow.